This version follows one strict teaching rule. For every evaluated quantity, we show tensor notation, then indicial notation, and only then the numerical example. A scalar is order 0. A vector is order 1. Stress and strain are second-order tensors. The gradient of stress is a third-order example. And the stiffness tensor is fourth order because it maps a second-order strain tensor to a second-order stress tensor. We will use one fixed stress tensor, one fixed strain tensor, and one unit normal throughout. Index notation is the safest language for tensor algebra. Repeated indices are summed, and free indices remain in the result. We start with vector operations. The dot product returns a scalar. The cross product returns a vector. And the dyadic product returns a second-order tensor, with each entry formed by one component of A times one component of B. For second-order tensors, the transpose swaps indices. The trace contracts the diagonal. And every tensor can be split into symmetric and skew parts. In classical small strain solid mechanics, stress and strain are symmetric. A single contraction gives the traction vector when stress acts on a plane normal. Matrix multiplication of two second-order tensors gives another second-order tensor. A double contraction returns a scalar. And that scalar appears directly in the strain energy density. A dyadic product of vectors gives a projector. A dyadic product of second-order tensors gives a fourth-order tensor. In linear elasticity, the fourth-order stiffness tensor maps strain to stress. Every second-order tensor splits into a spherical part and a deviatoric part. The spherical part governs volumetric response, while the deviatoric part governs distortion. For invariants, we first write the tensor quantity, then the indicial definition, and only then the numerical value. We begin with the full stress invariants and the deviatoric stress invariants. We then follow exactly the same sequence for the strain invariants and the deviatoric strain invariants. Principal values come from the eigenvalue problem. We first show the tensor equation, then the indicial form, and then the computed principal stresses and principal strains. Traction on a plane comes from stress acting on the plane normal. Its normal part is a scalar, and its shear part is the remaining vector after subtracting the normal projection. The key discipline is consistency. First show the tensor object, then write the indicial form, then evaluate numerically. That keeps the mathematics transparent and prevents notation drift.